welcome and good morning and good evening or whatever time you're in if you're watching it online. So I'm here to give you a little bit of a technical walk through Ballerina, just to give a understanding of what the language is, what we're trying to do, and why we're doing it, and so forth. And also to hopefully convince you before when we're done that this is really not Java. Somebody had tweeted this morning saying Ballerina looks like the child born of a cross between Java and JavaScript. And it's not at all that, so I will hopefully get that out of the way. All right, so let me just start with one slide of motivation. The first part I'm not going to go through. I think if you are in this conference or you're familiar with sort of why there is a change in the way the world works and that why there is a need for a certain kind of computational things to become easier. And so I'm not really going to worry about that part in this conversation. Let me talk about the second bullet a little bit. One of the things that's happening in computing in general now is this idea that everything's becoming smaller. And what we run on, how we run it, everything is becoming smaller. So if you look at the place where we run code, when I first started with computing, you had actual box and you would run something on that computer and there was nothing else between your program and a little bit of the operating system and then the hardware. Then we went to virtual machines, we went to containers, now we're going to serverless. There's all this sort of everything being abstracted away from the programmer saying you just focus on the little bit of code you need to write and everything else will get taken care of for you. Right? So it's sort of a minimalization on the hardware side. On architecture, we have this concept of service-oriented architecture has been around for a long time. Now there is microservices, which is almost the same thing, but the idea being you break it up into smaller and smaller pieces. So granularity of composition becomes smaller. And ESB, which is sort of the fundamental way in which integration is done, there's a distributed concept now called service meshes. So everything is becoming smaller. And then what does that mean in terms of how you deploy software? So I started the company with Paul in 2005. At that time, middleware was something that we believed as a long-term path for how you would separate what we can do for the programmer versus what the programmer does for the business logic, and then everything gets taken care of by the middleware. But if you look at what's going on with serverless and service mesh and microservices and so forth, there is no app server. Tomcat was the number one app server that everybody talked about. If you look at the microservices world, no one talks about Tomcat anymore, right? It's gone, basically, because there is a little bit of service handling, HTTP code or whatever you need in the code you deploy itself, and you don't have an entire server. So what's happening is this approach of middleware, where there was a server running, and they would run your code, is pretty much gone. And in the service mesh kind of approach, it's now going to a model where you have a cousin nearby, which is this concept of a sidecar in a containerized environment. There's a corresponding bit of support code running for you, and it's small, it runs efficiently, and it runs next to you. And what I see is this process going even further to the point of saying, let me just write the code and don't want to worry about anything else. Everything else gets taken care of, orchestration infrastructure that you're running under. And what that kind of means is there is no middleware. Middleware is dead, but it's actually middleware is everywhere instead of it's not gone, as in the supporting infrastructure that middleware gives for code is not gone, but it's just not something explicit. All of these factors together, what we believe is that what this suggests is that the way we program applications today with Java and Go and Rust and whatever the language you're programming in, or Python, doesn't matter, are not really suited for this problem because they don't really address these kind of scenarios in the first class way. And that's why we wanted to create Ballerina. So one key design motivation for Ballerina came from this idea of sequence diagrams. So what we found, Paul mentioned this also, that every time there's a complicated problem to talk to a customer about some scenario, we always draw a sequence diagram to explain this is what's going on. We also use sequence diagrams to model problems before you start implementing and saying, this is what this guy is doing, this is what this other person is doing, let me hook them all up and show you how they're interacting. But when it comes to code, that goes away and we start writing code in a different way and you kind of completely lose the sequence diagram. So fundamental abstraction for Ballerina is why not use that as the way in which you program? And really, and as you go through this, you'll see there's a bunch of things we've done that have adopted that, and what that means, Paul showed a little bit, that you basically get a picture for your code free of charge. Right? You can see the code completely in a sequence diagram, and of course it comes at a price as well, so I'll talk a little bit more about that. Now let me kind of cover some design principles in how we have designed the language and what that implies, you will see as in a little bit. So the first is that we wanted to have an approach where there was lexical, normal, textual code, as well as a full graphical representation of that code, exact parity, and not a picture. As in, the picture that you see is the code. It is not something else. There is no special thing we save saying, here's how we draw that out. It is exactly the code. And maintaining that required certain design compromises, design features that we are forced to follow in order to achieve that. So it doesn't come free. So there are some lexical constraints you have to follow in order to achieve that. But it gives a lot of benefits, so we want to adhere to that principle. Next one is one of the fallacies of distributed computing, that network is something that you have to understand is something that can fail. So trying to hide the network is a problem. And many programming languages don't have, the language itself doesn't have a concept of network abstraction, network programming, network concepts into the language. They're just libraries. If you look at Java, there's a class that does all kinds of stuff. And as far as the language is concerned, it's just a regular old class. It has no understanding that this is a different kind of thing. So we want to make so the first, those 3 bullets are related to network, are all about saying the network is an important part of the problem, and you cannot just ignore it and say it's just another library function that you call, and they're all equal like everything else. So there are a bunch of abstractions in Ballerina to make the network first class in various ways, and we'll talk about that. One of the other things that if you're a Java programmer, you're familiar with something called find bugs, and there's find security bugs and a bunch of similar tools in various languages, which are essentially tools that were written to deal with the fact that the language allows the programmer to screw up. And then this tool comes and says, well, you really shouldn't write code like that. So Ballerina's design principle is a bit different. Well, if you really shouldn't write code like that, the language won't allow you to write it like that. Right? So the compiler is a lot more opinionated. The language semantics are a lot more opinionated, saying, if you write code like that, you are likely to have a problem, so we're not going to let you write code like that. Sorry. Right? So there's no other tool. So we don't want to leave room for somebody else to come and fix the things that we should have done in the first place. Right? So there's a lot of stuff that we're trying to do, and this is coming from all the experience we've had with working with all the different things, to say, when you design a language now, we should just make it so that when you write the program, if it compiles, hopefully it'll run and there won't be any problems. When you talk about network services and network abstraction, security is something you cannot ignore. It's not an afterthought. It cannot be an afterthought. So there are concepts in the language that were put in order to make every program you write in Ballerina always secure. Now this is difficult to achieve, but there is a bunch of stuff that we put in order to make programs secure by default, right? So you don't think about security later. When you write the program, you have to understand if you're dealing with network stuff, it is not going to be secure. And if it's not going to be secure, when you deal with the data, you need to process it in a different way. So there's a bunch of stuff done like that. And then a particular programming paradigm. So when you look at a language, people ask you, is it an object-oriented language, is it a functional language, is it this language or that language? Ballerina is not trying to be X or Y language. Ballerina is trying to take the best concepts of object orientation, functional, and various other kinds of things, and bring it all together and try to package up a set of features that we hope are the right combination of features. Right? So if you look at what Java did back in 25 years ago, it was something similar. C++ had all kinds of stuff. If you're old enough to remember C++, there were 15 ways of doing different things, all kinds of powerful things. And it was really difficult for a programmer to use that stuff. Java just abstracted that away and came up with a much more simple set of things that brought together lots of concepts from various languages, including Smalltalk. And we are trying to do something similar. And the other thing is, this is not a research project. So there are no new programming language concepts in Ballerina. We are taking concepts that are well proven, well understood, that have been implemented in various programming languages, various different programming languages, and trying to put them all together into a single architecture so it works all together. Now my next slide is a long slide of things that I think are unusual about Ballerina, and this is what I'm going to talk about. I'm not going to talk about the stuff that's usual about Ballerina. Let me just go through the list. Some of them I have a lot of details. Some of them I'm not going to talk about because there are other talks. Some of them we'll just leave it for people to read about. Let me just start at the top, structural type systems. I'm going to talk a lot about the type systems, so let me not spend more time here. And the first few things I'm going to talk somewhat detail about: the application level abstractions for networking, the graphical sequence diagrams, the parallelism stuff, and so forth. Errors and exceptions. this is a problem area for almost every language. If you go back to C, if you remember, every system call in C usually returns -1 as when something goes wrong. And what that meant, and then there was like error number or something else that would let you get some more information. And that was basically saying, well, -1 is a value outside the expected value space. So if something goes wrong, you can check whether something is there. Go has this concept of multi-return, and if you have an error, you're supposed to have a second return value, which indicates that it's an error. That's also a problem because if you don't check the second value, you can get the first value and keep on going even though there was actually an error. So Ballerina makes the concept that something is going wrong a very common aspect, and we do a lot of effort to say errors are first-class things. Errors are not something else that happens. So errors are a special kind of value. I'll talk briefly about that. And there's a way of handling them, and they're not something you can ignore. If something goes wrong, you have to deal with it. There is a concept of exceptions. Right now, syntactically, it looks like try-catch. Actually, we are going to change that probably, just to get out of a little bit of the Java mindset on that. But exceptions are things that are supposed to be used when there's an exceptional situation, not a regular error situation. In many programs, something not being able to give the right answer is the normal behavior. That's part of the function signature. So we make it part of the function signature in the design. Concepts of traditional middleware, like what we have as products, API management, ESB-like integration, data integration, analytics, identity, all these fundamental components of the runtime aspects of those are burnt into the language in various forms, either as library extensions, part of the standard library, or as things that you always have available in the language itself. I'm not going to talk much about that. There's a whole bunch of examples in the Ballerina by example site that goes through that, and a lot of the talks today will cover a bunch of those things as well. The next bullet about language extensibility for deploying into different environments is kind of important. There's actually a full talk on that, but let me just briefly mention that. Some time ago, when you wrote a program, you take the program, you compile it, or whatever, you give it to the interpreter, and you just run that program, right? And it just runs on a shell somewhere. It opens a process and runs that code. But now, when you write a program, you try to run it, we no longer just take a program and just run it. We might take a program, make it into a Docker image, take the Docker image, put it into some kind of container management platform, run it on that. We might also have all the way up to Kubernetes, or maybe deploy it into a cloud environment, and so forth. So the problem of building and running a program is very different now. Building also involves having to deal with all these environmental features of what is the environment in which I'm going to run on. And the traditional way we've dealt with this is to say, well, that's not the programmer's problem, that's somebody else's problem. But in reality, if you write a program that runs in a complicated environment, the behavior of that program is different from running in a simple environment. And so when you write that program, you have to be aware that I'm running in a serverless environment, I'm running in a container environment, I'm running in a cloud environment where persistence and state have a different meaning, etc. So taking that away from the program and telling the programmer, you don't need to understand that that's somebody else's deployment problem, is not a good thing. And writing that in a YAML file, or which is the popular version now, but or XML or whatever the deployment config is not the right way to do it. So what we've done is brought those into the language and make it so when you write a program, you get to also instruct saying how this is going to work in such a deployment environment. Obviously, that is an extension because it's a platform-specific set of things you need to have. There's a talk on that, so I'm not going to get much into that. Integrated language query and streaming query. So C# introduced something called LINQ, Language Integrated Native Query, which is a way of bringing SQL-like query into the language. Ballerina has something very similar, but it's also not just a static query, but also streaming query. And again, there's a talk on that, so you can learn more about that. Security abstractions, I mentioned this a little bit ago. This is an important one, trying to make it so when you write a program, the program just runs, and if there are any things that are insecure, the compiler won't let you compile that code, right? And again, there's a specific talk on that, so I won't get into the details of that. I want to briefly mention this next bullet, the event-driven runtime concept. So if you're familiar with Node, in order to get performance, the reason Node is so popular is because you can write really high-performant programs. But to write that performant program, it's a nightmare because you have to write callback after callback after callback in order to get your actual logic to run. I mean, if you come back 6 months later after a Node program you've written, you have to spend several hours trying to figure out how exactly this thing works because it's like a nightmare. And it's there in order to get the performance. So Ballerina takes a different model. The entire Ballerina runtime is non-blocking, event-driven. So you just write a normal program. You think you're just saying, okay, do this and then do that. But underneath, nothing ever blocks. No resources block. right? So the runtime is completely non-blocking. So you can program like a normal sequential step-by-step program, but underneath there is no resource locking going on. We make sure we release everything. So you get the same performance behavior that you get in a node program, but you don't get the programming complexity that you have in that kind of model, right? This is in order to do this, we obviously have to do all kinds of dances because we are currently building on some libraries that are not non-blocking, so we have to do like thread pools here and there to manage that. But we are in the process of basically rewriting all of that, so we won't have that level of stuff underneath. The other thing is when you write a program, there's a bunch of things when you design a language that are afterthoughts. Things like version management, documentation, dependency management, testing, etc. are not part of what language designers consider when you design the language. You see this in Java, you see this in Rust, you see this in Go, and so on. We've taken very opinionated views of some of these things. So for example, documentation. Documentation is actually, there is syntax for documentation in the language. It's an extension of Markdown. We are in a transition phase, so we have a new version of that syntax coming up, which is not fully implemented yet, so it's a little bit of stuff here. But the documentation actually gets semantically validated. So we check that if you have a function with 3 arguments called ABC, that actually you are referring to ABC in the documentation. And if you go and change the function and add a D to it, and D is not referred to in the documentation, you'll get a compile time error saying your documentation is out of sync with the code, and it won't let you compile. Right? So this is kind of annoying, right? But it's important because documentation, of course, we only do this for public symbols, but that's just a choice we made. So if it's a non-public symbol, we don't really care. You can do whatever you want. For public symbols, we force you to document something. Now, obviously, the lazy programmer will just put that name and be done with it, right? So we can't stop that. But documentation is an important thing because, especially for enterprise code, our experience is that people write the code once, and the same code gets maintained and read 50 times over the next 10 years. Right, or 5 years. Nothing ever goes away in enterprise code. It just keeps evolving. And so making it a little bit difficult to write the code up front, making it a little bit more painful to write the code, but getting a higher value result out of it is worth the effort. That's why we're taking these kind of positions on documentation. And there's a bunch of other things I'll briefly refer to that touches that point. Version management. Lots of languages don't think about versioning and dependency management at the point of designing the language. So we've done a lot of work on that. The Ballerina Central that Paul showed is a component of that. There's a whole package management model. There's a version management model. This is not all fully implemented yet, but we have a full design for how we will do versioning and package management. Because you can't these days, when you write a piece of code, it is very natural to, first of all, consume other people's code from somewhere else, as well as produce code for other people to use. And so if you're doing that, you must have a namespace management model, you must have version management model, otherwise it doesn't work, because it just gets a collision and you get a mess to deal with. Testing also, there's a talk about that later too, about how we're doing for testing. All right, let me spend the rest of my time on the first few bullets to give a little bit more detailed understanding of what's different about Ballerina at a core level. The first thing is related to the type system and how we deal with values. So I'm going to introduce this concept of values and then talk a little bit about the type systems. There are different kinds of values that you can operate on in Ballerina. There are the 3 fundamental kinds: simple values, structured values, and behavioral values. Simple values means sort of literal values, single things. The open close parentheses is for the value, special value called nil, which is there's no value basically, it's empty value. Boolean is Boolean, int is int, etc., right? Structured values are things that have some structure. They are combinations of values which become a new value. Now, and behavior values they have some data and some behavior, and let me get into them a little bit more detail. Let's talk about simple values. By the way, I majored in graphic art in college, as you can see. Minored, rather, sorry. I didn't do very well. And so values in Ballerina are classified according to the kind of values they are. So string values. Now, if you notice the particular 2 words I chose today, they're kind of popular today and yesterday. String values are strings, right? And they can be arbitrary length strings of whatever length you want. Floats are floating point values. So the primary value types that we have are strings, float, Boolean, decimal, int, and the empty value. Now, the empty value, there is nothing in that set. These are supposed to represent sets, by the way. So there's a set of values, and that is a set with no members. So it's an empty set, right? But it's useful in some places. We'll see as we go along. Decimal is decimal. Why are we putting decimal? Because JSON is decimal. If you really use JSON and you do JSON numbers, JSON specification for numbers is actually decimal. So if you don't keep them as decimal, you're going to mess something up. If you get 10.00, it'll go out as 10 point or 10.0, and it's not the same thing if you're dealing with numbers that really pay attention to that. So these are the basic simple values, right? The things that are the ultimate, like the atoms of how we build the entire type system in Ballerina. The next one is structured values. Now you take these simple values and you group them into various kinds of structures. So mappings are structures with a key value pair model. A mapping is like a map. It's a collection of name value pairs, and any collection of those is a value in the mapping set. And you can have any number of those sets, obviously, there's an infinite number of these things. Lists are ordered sequence of values. So they can be arrays are lists, tuples are lists. So they're ordered, that is, they're positional. There's first one, second one, third one. Mappings are not positional. Mappings are based on keys. There's some kind of a key that gives you the value for that thing. There's also XML. XML is a primitive value in Ballerina. I'll talk a little bit about XML in a bit. Also tables. Tables represent essentially 2D arrays of values, obviously used for SQL-related kind of things. And errors. Errors are also special values. I didn't write a sample in here. So behavioral values are things that represent particular behaviors. A function value is an actual function. It's not an invocation. It's not a representation of the code. It is the value of the function that you can pass around and so forth. Right? So functions are first class in Ballerina, so you can do full functional programming in Ballerina. Future represents a invocation of a function that's already started off that you can go back and get information from while it's running. Objects are objects. Stream is a particular way of dispatching data to multiple participants. Type descriptor is a meta type. It's a type descriptor is a value whose value is a type name, basically, a type. And there's a few more that will be coming as you go along. Now let me talk about type descriptors. So I only talked about values, right? So values are how you actually just write down something. And anything that you write in the program is a value that you're dealing with. Ballerina is a structural type system. What that means is we have this concept of a type descriptor, which is a description for a set of values. Okay? So a set is a set of values. So the set can be a finite set, an infinite set, whatever. So what a type descriptor is a membership test for a set of values. So you can say, oh, this is a set of all integers. And then there's a type descriptor called int, which represents that set of values. So the type itself is a label. It just says, oh, this is the name for that set, right? So you remember now, because this is just values and different sets that I'm defining, I can take a given value and shove it into any number of sets. Right? Now obviously I can't take an int value and put into a string set because that's won't satisfy the membership test. But I can define a new set and put it in wherever I want. Basic types like int, string, float, etc. are names for the fundamental value sets. So these are predefined names we've defined for the fundamental kinds of values. So you don't have to go and define what an int is because you really can't, because you can't list them all out. So we've defined those and say if you use the word int, it means it's one of these IEEE 64-bit integers, blah, 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 right? And there are type constructors for creating values of the various kinds of structures. I'll briefly cover that in a minute. There's also a concept of a broad versus narrow type. So let me explain that. If you look at that line of code, string s equals x, because x, I guess I should talk about singleton types, but the value of x can be actually one of two things. It can be, because it's a set, remember, a type is a set of values. I can take that single value x and put it into a set and say, okay, it is that type. It's of a type that can have only exactly that value. But in this case, I have said it's a string s. So there's a contextual type here that says, okay, variable s is supposed to be a string. That means I'm going to interpret x in its broader context of that it's okay, it's a member of the string type. Right? So there's a concept of a narrow type and a broad type, and this comes into how the type checking system works and so forth. Okay, let's talk a little bit about mapping types. Mappings are very useful and very important and used all over the place. So these are like records, structs, and so forth. They're just collections of name-value pairs. So there's some kind of a key and a value, and the key is always a string. And we have two different type constructors for it, record and map. And there is a concept of open versus closed mapping. So let me explain that. So an open mapping means something like a hash table is an open mapping because the number of keys that you have in there is not fixed. You can have any key. You can put any number of keys in there. Something that looks like a struct in C or a class in C++ or a Java class with public fields, let's say, is a record, which is a mapping with a fixed set of fields, right? You name the fields and say these are the fields, right? So there's two aspects of a mapping. It can be open or closed. There's also a concept of required versus optional fields. So you can declare a mapping and say this struct, this record has a field called foo, and the field foo may not be there. You can put a question mark at the end saying it's optional. What that means is if the field, and it has a type, let's say it's int, so if it is there, its type is int, but it may not be there. Why is this useful? So if you're trying to describe some data that's going on the wire that sometimes has optional fields, sometimes has fields that you don't deal with, you can fully describe that in Ballerina now, right? So the type system is very rich, and you can describe much more than you can in a traditional sort of programming language, and lets you describe all these things. So the difference between record and map is basically a map is a mapping from string to values of a particular type, and a record is mapping from string to one by one you list out the types that you want to have. And if it's an open, you can put more stuff, right? There is some set of covariance and subtyping. So when you have a subtype of a mapping, the subtype, a map, if you have a type, so if you have a map of a particular type, and you have a subtype of that type being put into it, so it's considered covariance, which says that the mapping itself is also a subtype of that, right? So in order to make that work, we have to maintain something called a storage type. It's a little bit similar to how Java arrays work as well. That has some baggage, but it has some runtime costs, but it's the most sort of natural thing for programmers to do. The other collection type is lists. So these are like arrays and tuples. They're ordered. So instead of mappings which are accessed by key, this is accessed by position. So you say, give me the 0th one, the first one, second one, up to n minus 1, where if there are n items in the list. And can also be both fixed length and variable length. Fixed length means you have set the size, you declare an array of size 10, or a tuple of a particular number of items. A variable length means it varies. The array constructor, the one where I use a normal array syntax, that one has a single member type. So you can say it's an int array or a foo array or a bar array. And it can be a fixed length or a variable length. There's syntax for doing that. A tuple constructor, on the other hand, a tuple is a combination of values, fields. So you specify what each one's type is. So it's different kinds of member types, but it's a finite and fixed number of items. So the XML type, XML is a primitive value kind in Ballerina. So XML has been around for a long time. If you've been doing any kind of integration for a long time, you would touch XML. Now XML is not that popular. Most people are using JSON for stuff, but XML is still very important. And you can't build XML as something else and get a native behavior. So XML is a very particular kind of value in Ballerina. It's a predefined value. And the model that we followed for XML is also a little bit different from the traditional way in XML is modeled. So by traditional, I mean something like DOM or any kind of data binding kind of model. Ballerina has XML values directly, and we have sort of a different model of how we do it. It's not a tree model. It's a sequence of values, each one being an XML item, and the same, anyways, there's a bunch of stuff there. And there's also syntactic support. So you can navigate XML structures by saying a.b.c, and it's going down a little bit like the XPath, like syntax of going down to access different fields of the XML. Right? There's also literal XML, so you can put XML values in the language. It's reading and writing as well. Tables, tabular data, you need tabular data in lots of things. It's essentially a 2D array, and also ties into all the database connectors that we have. So if you have a database connector, what it returns is a tabular value, and you can also query that table using the integrated query capabilities. I mentioned errors. Errors are a thing in its own space. We have a set of different there's a new value space called for errors. So if you return an error value, you can never overlap that with a normal return value because it's an entire different kind of value, right? And errors have a particular behavior, so they have a reason string, so have some details. It's basically a tuple, so you can have a custom defined set of data as the map, and also a stack trace from where it was created. Okay, and there's a few other things that I need to talk about in the type system, so let me go through that so you understand. So unions are very important. Paul briefly mentioned this as well. a union is, if you think about sets, it's very easy to understand because union just says the union of two sets, right? Two or more sets. So you just name the sets and you say, I have a new type defined by union of set 1 and set 2, right? And that's it. Syntactically, you just say A or B like that, and then you can assign to that variable any value from either set, right? Now, obviously, this comes, now we have to figure out, okay, how do you access it in a type-safe way? We'll get into that in a minute. I mentioned finite types briefly. So it's just a set of values, so you can have any finite number of values as well. I can declare a set and say, it's these values. So here I declare a type called this or that, which has the string this or that. Well, I should have said all 17, but all the values 17. That means a variable of this type can have any of these three values, and that's it, no other value. So it's like an enum in some sense, but it's a super powerful enum because it's actually type checked for exactly those values, and you can do a little bit more with this. Optional types are important. So optional types are a way of dealing with null. The fact that sometimes you have, what you have in a variable is a reference, and the reference may not actually be holding a value. It's fully generalized in Ballerina. Optional types can be for any type. So it just says you have a storage location and it is holding a value of a particular type, or it's not holding any value at all. Right? So it has no value, so you can't access it. So if you declare a variable as int question mark foo, you have to check whether it is actually an int or it's nothing. And if it's nothing, there's nothing, so you can't get it. Right? So with this, there are no null pointers in Ballerina. You cannot get a null pointer issue in Ballerina because there is no concept of null in the language. Okay, we talked a little bit about JSON. So with this machinery, what happens is JSON just falls out. You don't have to do anything. JSON is simply a union of some built-in stuff. Actually, int or float should be changed to decimal to be more accurate. This is a little bit older. And that's it. So we don't have to essentially do anything for JSON. It just falls right out. Now, we don't implement it fully like this because we haven't done recursive union stuff yet, but we will have to do that at some point. JSON objects, which is what most people think of as JSON, as curly brace something, that is just a map of JSON values. Right? But it turns out JSON is more than that. If you send the number 10, that is actually a JSON value. Because maps are these mapping types with open, can be open records with optional fields and so forth, you can do lots of interesting stuff with JSON now in Ballerina that you cannot do in most other languages. Right? Also, it's important, the last word is important. There is no concept of data binding needed in Ballerina at all for JSON or XML things. So if I'm reading some data from the wire and it's actually some JSON value, if I give a schema for it, if I declare either a map or a JSON thing, if I just say JSON, it just becomes JSON, there's no data binding. If I want to actually name the fields that are in there, I can declare a mapping, I can declare a record and say it's going to have this field, maybe it has this field, and then it has a collection of stuff, and after that, I don't know. Right? I can declare that record, and when I read that JSON value, the JSON value is that map. So it's not and so it won't read into that. It will get a type error at reading time if it doesn't work. Right? So the code doesn't have to deal with, oh, did I get all the data? If I write that type, it is exactly that. If that function gets called, it's that. It's nothing else. Right? So there's no considered data binding needed in Ballerina either. I mentioned byte. So byte actually is again simple. Byte just happens to be predefined union as well. It's a union from 0 to 255. That's it. Right? So it's integers. It just happens to be a finite set of integers that we allow. By doing this, you avoid all the problems that Java has of having to do math on byte and how you do byte plus short plus int. None of those problems exist when you do it like this, right? Byte is just a number. It's just a number. It happens to be a number between 0 and 255. If it's more than that, it's no longer a byte. So byte is a subset of the int space, if you think from a value set point of view, right? So it's very easy to manage it like this. There's also a predefined type called any, which is just an alias for union of anything, right? Any user-defined and built-in types as well. All right, let me talk a little bit about casting and conversion. So casting basically means taking a given value and treating its type as something different. So from a set point of view, it's very easy to understand casting because values never move. The value is a single thing. So all you're asking is this value a member of this set? That's it, right? So and a given value can be in any number of sets. So casting just means, oh, I thought it was in this set. I'm going to ask, can I treat it as if it's in this set? If it is, it's castable. If it's not castable, right? So there's some concepts of safe casting, unsafe casting, basically whether we can statically tell whether it is castable or not, or whether we have to do it at runtime. So there's some stuff that we are still working on to finalize that. Ballerina does not do any automatic type conversions, not even into float. Right? So the rule is we're not doing any automatic type conversions. So it makes things, the programmer has to be aware that you're doing these kind of things. Zero, basically, on type conversion. We had a thing called transformation some time ago. We took it out. We have to bring something like that back. There is a need to have a more convenient data transformation kind of thing. So we have some stuff that we need to put that in at some point. Okay, so let me talk a little bit about some things that you have to do when you have unions and all these complicated things. Unions are great, but when you have a union saying I have a variable of type T1 or T2, I can't safely access it, because if I access it, it could be T1 or T2. So there's a concept of type matching, which is now quite popular. I think Rust has it. There's an extension for ECMAScript that's proposed for TypeScript to do this as well. And what it says is, okay, at runtime, check the type. Based on that, there's a type descriptor, and if it matches, that's a code, right? So effectively it says, oh, this is now of this type, so I will interpret it in that way. So if you have a union, you have to match all the cases, then you can handle each case. And there's a way of doing that within an expression as well. So errors are great to have errors all over the place. So because we force you to return errors specifically, typically functions return type of function is always like some t that the function wants to return, some type t, or it's an error. Now, this is annoying because now I can't use it directly, because now I have to match it, right? It's a union. If it's a union, I can't get the return value. So there's some stuff to do what's called error lifting, which is to take the error and get it out of the way, because I'm not expecting an error, let's say. So I can say check an expression, and what it'll do is if it's an error, it'll just return that error from the function, and then convert the type to being the type minus the error. Similar concept for nil lifting. So nil, so if you have deep structures, if you're like a.b.c, it's very annoying, because now you have to keep checking, because we don't allow you to have a null pointer. You have to check, is that value there? If it's an optional value, is it there or not? So nil lifting is a way of saying, when you do a.b.c, we automatically check that for you, and if it is not there, we'll just handle that case for you. So in Ballerina, when you write a.b.c, the compiler code gens like 15 lines of code to make that work. Right? So it has to do all these things of actually checking it. And there's something called nil and error lifting, both using exclamation mark. You'll see this stuff later. Okay, let me switch gears. Enough about talking about the type system. Let me talk a little bit about the network and abstractions. The network is an important thing that we want to model correctly. So we have a couple of key abstractions we're using, something called endpoint. Endpoint represents a network termination point plus type-specific interactions that you're allowed to do with that. So in most languages, we represent network stuff as an I/O channel only. So there's like a socket or whatever the mechanism, but it's just an I/O device. You can do read, write, open, close on that thing. Ballerina says, no. If it's a low-level network channel, that's all you can do. But if it's like an HTTP network channel, there's a higher-level abstraction that you interact with that. Right? Those are the actions that you can do against that. So that's an endpoint. So endpoint is a network termination point plus the behaviors that you can have with that endpoint. And so it can be ingress or egress, like incoming or outgoing. If it's incoming, there's a different set of behaviors. If it's an outgoing one, there's a different set of behaviors. And all of this gets modeled, now coming back to the sequence diagram concept, this gets tied into the sequence diagram. So if you look at this picture, let me talk about so also any interaction with the network, Paul mentioned this too, we want the programmer to be aware that I am making a network interaction. So there's a syntactic difference that we force, saying talking to an endpoint is different from talking to a regular function or object or something. Right? That's using an arrow sign. So when you do an arrow sign, that allows the graphical editor to show that endpoint as a separate thing and draw a line for that. Right? So this is all part, so this becomes, so it's actually two things. We want to be able to draw the picture. In order to be able to draw the picture, we need that syntax, plus we want to force the programmer to think that it's different. So again, we need that syntax, right? There's a bunch of stuff. There's a talk about resiliency and building reliable services, so I won't get into that. There's a bunch of stuff that you need to do if you're doing network programming to make programs work reliably. Ballerina has a whole bunch of things for doing that. Services are the second half of the endpoint part. So if you have an ingress endpoint, something that's coming into you, you need to be able to handle the stuff that comes in, and it comes in periodically. It's not synchronous usually. So that's the abstraction of a service. The service is the callback handler basically for network interactions coming over the network, except because it's an endpoint, it's typed. It has particular behaviors. So the resources have an expected signature. There's a particular semantic, and you have to implement that particular one, and then the endpoint knows that this is exactly the one that can handle a particular request. And one other point we make about how you program services, if you're familiar with JAX-RS or any of this sort of convenient way of writing web services, the way you write a web service, you write a function, the function return value becomes a response of the web service. But the problem is, and then if something goes wrong while sending the response, the function thinks it completed, because the function returned it, the framework sends a response. And unfortunately, in the way the network works, you can't depend on that. The response sending can go wrong. So in Ballerina, you can't do that. If you want to send a response, we give you the endpoint with which the connection was made, and you have to explicitly say, I want to reply through this action. Right? So if you start learning about HTTP2, you will see HTTP2 is a much more bidirectional protocol than HTTP1. So you can send promises, you can do all kinds of stuff. It's not just a matter of, here's the answer. So the Ballerina HTTP2 connector takes care of all of that and gives you a bunch of actions. So you can just call that thing. So your code will simply call whatever the thing you want to do there. So just a quick comment about the graphical notation and the objective of the graphical notation. So there's all these low-code kind of environments. There's everything from Boomi to Jitterbit to SnapLogic to all kinds of stuff. That's not what we're trying to do with Ballerina's graphical notation. It is a programmer's graphical notation. It's a sequence diagram. Each worker is just regular code, so you can go into whatever level of detail, but we're not trying to make it a non-programmer's tool, right? Ballerina is a programming language. The picture is a programmer's tool, not for non-programmers. Let me talk briefly about parallelism. So pretty much every programming language has the semantic that when you start the program, main or something equivalent to main starts, and one thing starts running. Right? That's how we all learned how to program in pretty much every programming language. That's not the way in Ballerina. In Ballerina, a function, an executable thing, a function, method, resource, can have any number of parallel execution contexts, and they all start running. And they just run independently and concurrently. So here's just a random useless bit of code that shows you two workers, both of which, when this function is called, they both start running, they both get the incoming parameters available to them, and they both start executing concurrently. And then in this particular case, I'm sending some random number 10 from one worker to the other worker, and the other worker receives into a variable. It doesn't really do anything with it in this. This is some silly example. But what this shows you is that the model of parallelism in Ballerina is fundamentally different from parallelism in pretty much all the primary languages, because parallelism is always like a master and a bunch of slaves model. That is, there is some one person, and then in Go, you start a Go routine. In Java, you start threads. Here, there is no such abstraction. The only abstraction is sequence diagrams. And each worker is a concurrent piece of code. And you just write any number of concurrent things, they all just start running. Now, if you think a little bit detail about how in the world does that function behave, so it becomes a little bit complicated. What is function invocation now? When I call a function, multiple things run. When is that function completed? And so forth. So there's some stuff that comes out of that, and we are still getting this right. So it becomes a bit complicated. But and asynchronous functions also a little bit similar. You can start a function, and what that means is just fire off all those guys, and at some point later I can check in on it. I drew one line just to show worker-to-worker communication. This is actually an important problem because, so this is how you have, so if you have parallel things running, you have to be able to communicate. And then when you communicate, a common problem is you can have a deadlock, right? Because I'm going to wait for him to send me something, but he never sends me something. Right? His code was never written to send me something. So we have a way of catching that. Right now we have some restrictions with some improvements that we were planning to do so that when you finish, so there's sort of an interaction signature that we compute, and they have to match. If they don't match, again, compile time error. Right? So there's some stuff that we're trying to do to make that fully work. Okay, last two slides. So just a quick statement about the implementation. So the way this is all implemented is we have the language, we compile it, we parse it, we build a tree, blah, blah, blah. Eventually it comes down to a particular intermediate representation, which we call BVM bytecodes. That is the sort of a portable representation of a Ballerina program, machine-independent, platform-independent representation of a Ballerina program. There's also an extensibility architecture in the compiler that when Lakmal talks about how we do the Kubernetes stuff, he will explain a little bit. There's a language server, that is how we do all the IDE stuff. And then to actually run the program, there is currently a Java-based interpreter for that intermediate representation, right? That's a temporary statement. There is no connection whatsoever to Java in the implementation of the semantics. We're in the process of rewriting that in LLVM as well, using LLVM as well. All right. Very quickly, some work that's still going on. There is some concurrency control stuff in Ballerina. There's a lock statement that lets you do some stuff. It's not powerful enough. There's some more stuff that we're working on, try to improve that. There's a few things we're working on to support long-running behavior. So for a program to be able to checkpoint its state and continue execution, this is so you can write workflow-like scenarios in Ballerina. That's also making good progress. And a compensating transaction component as well. We have a 2PC transaction that Aziz is going to talk about. There will be a compensating one coming up as well. There's some work we're trying to do to make the Docker and Kubernetes stuff support composite applications, and we won't talk about that right now. Generic types are one big thing that if you look at the type system, there's one big type system component that is missing yet. That's on our list to get done. Internationalizing the grammar, this is a favorite one for me. Every programming language is written in English. You have to write the words in English. There are a lot of people in the world who don't speak English, for whom the word service and function and worker and so forth have no meaning. And there's really, the language doesn't give an ass, right? It's just a text. Just give me a node that has that thing. So we want to make the entire grammar available in other languages. So not just, of course, it's Unicode, so you can have strings and names in Unicode, but the entire grammar. There's no need to write function for. You can have, whatever the word that you want in various languages. And on the implementation front, I mentioned that we are in the process of converting to having an LLVM implementation. There's also something called WebASM, which is a way of running, which is like a sort of an abstract machine that runs in a browser. We want to target that as well and target all kinds of different environments. All right, last slide. So Ballerina is trying to build a real programming language. It's not an academic effort, and it's trying to build it in a way that is first-class suited for a world with network being everything. Every call you make is a network call. The system calls are network calls, and so forth. And to make that work, there's a bunch of things that we're doing. It is completely open source, so I hope everybody who was interested will participate. There's mailing lists, there's Slack channels. We'll keep posting that out throughout the course of the day. And thank you very much.